James on cue gets it started in the recording. So good afternoon, everybody. Happy Monday. And today's Viceroy's seminar, CISR seminar, will be by Andrew Genter from Waterfall Security Solutions on industrial cybersecurity. Ask different questions. And I think this is a really, really important topic, particularly as a grid person. Looking at industrial control systems and operational technology, or what we call OT, is much different from information technology, or IT. And these systems, in many ways, they're different. There are deep differences as well as superficial. So a little bit about Andrew. He's the VP of Industrial Security at Waterfall Security Solutions and is the author of 3 books on industrial security, the co-author of Industrial Internet Security Net Framework and UITP Guide to Rail Systems Cybersecurity Purchasing, and co-host of the Industrial Security Podcast. He spent a decade developing industrial control system products and half a decade developing middleware products to connect control systems to SAP, our control systems. The middleware resulted in a lot of OT networks connected to IT networks, and thus contributed to the cybersecurity problems that now plague many industries. He wound up as CTO at Industrial Defender, the leading developer of the world's first industrial SIEM. Now he's at Waterfall Security. Andrew leads a small team of experts who work on the world's most secure industrial sites. He and his team contribute regularly to cybersecurity standards and best practice guidance. Andrew has his bachelor's of science in applied mathematics and MS in computer science, both at the University of Calgary. So I think, is Andrew our first international speaker?
I would not know, but
yeah,
I am from Canada.
Yeah,
I'm
that's
sitting
what I
here
was
in
going to
Calgary,
say.
north
You're
of
in
Montana,
Calgary, so yeah.
South of Alaska.
So our first international speaker. So Andrew, I'll turn it over to you.
Thank you so much. Here we go. So yeah, oh, there we are. I hope you can see that. Yeah, so let's talk about cybersecurity. I have the privilege of working with many of the world's most secure industrial sites. The most secure sites also tend to be the most consequential, where, the worst can go wrong. And, it is their perspective that I document in the books that I write. They look at the problem differently. They ask different questions, and if you ask different questions, you get different answers. You see things differently, and it's that perspective that I try to capture in my conversations with these people and document for the rest of the world. Cybersecurity is a spectrum. It's a spectrum from engineering to IT style cybersecurity. It's a spectrum from consequence, from the least consequential, I don't know, small shoe factory is the example I'm fond of, to the most consequential, high-speed passenger rail switching system. If you mess with the control system, in the worst case, seconds after you mess with it, trains collide and you have a mass casualty event. So it's a different, it's a big space, and one of the problems with the space is too many people think it's one problem, when in fact there are dimensions to it that need to be appreciated, or we make mistakes. So let me start with the space. I understand many people here are not engineers. I'm not an engineer, but I've had the privilege of visiting this site. It is a small refinery in Europe. By small, I mean those tiny white specks on the bottom, those are automobiles. This is a small refinery. Okay, a large one is probably 10 to 20 times the size of this one. At industrial sites, we talk about cybersecurity. What is the priority for cybersecurity? IT theory tells us that we need to protect the information. We need to protect the confidentiality, the integrity, and the availability of information. You tell this to engineering teams and they look at you funny because their number one priority is not information. Their number one priority is safety. Don't kill anyone. Do not put the public at risk. Do not cause an environmental disaster. And their number two priority, once safety has been dealt with adequately, is reliability. Because these large, powerful tools tend to be very expensive. And if you want to get maximum return out of the investment in these very large, very expensive physical processes, you have to run them, you have to use them. And so unplanned shutdowns are a big problem, a big no-no. And, you know, the strange thing is you know, when you talk to engineers, they won't say that much about safety. It's the priority. Everyone lives safety, but it's so ingrained. You don't hear people talking about it as much. What they talk about when they're designing change to the system is reliability. Will this change trip the plant? Will that change, take us down? And the reason they're changing the plant is the third priority here, which is efficiency. Every engineering team on the planet pretty much has a budget this year to make some changes to the physical process to improve efficiency. Continuous improvements in efficiency, and a lot of modern efficiency improvements involve automation and computers. Continuous improvements in efficiency is why we have cell phones that we can afford. It's why we have drinking water that we can afford. It's why we have electricity that we can afford. So this is all important. These are the priorities, and they are characteristics not of the control system, but of the physical process. But we're talking about the control system. What is the control system? This is the control system from a waterfall customer, Detroit Water. I'm allowed to say their name. They gave us permission. Most customers don't. We're very grateful to Detroit. Um, One operator sits at this physical workstation, controlling the treatment of drinking water for 2.5 million people and the treatment of wastewater for some 7 million people. They treat the wastewater for a lot of the surrounding communities. One operator sits here 24/7. Okay, you're not allowed to run a large, dangerous physical process without human oversight in most jurisdictions. In most companies, you're not allowed by policy, and in many jurisdictions, you're not allowed by law. With a petrochemical pipeline, if the operator of a section of the pipeline loses control of the pipeline, the screen goes blank. And they cannot restore control in many jurisdictions within 30 seconds. They cannot transfer it to another operator. Here, you take this section of pipeline. They cannot go to a backup visualization. If they cannot regain control, visibility into the pipeline, by law, in many jurisdictions, they're required to lift the cage on the big red mushroom button and shut down that physical process because it cannot be run unsupervised. So this is what an operator sees, one operator 24/7, one supervisor looking over the operator's shoulder. When the operator goes on break, the supervisor sits down. There is always someone here. This is known as a human machine interface, screens and screens. Most of the screens you see here are summary screens. There are somewhere between 10,000 and let's call it 250,000 data points in your average industrial process. And what you see on a screen like this, there's no way you can fit 200,000 data points on a screen like this. You see summaries. And if you see a blinking red light saying there's a problem here, you click on that and you go down to a detail screen where you see maybe 2 more blinking red lights. You click on one of them, you go down again to a more detailed screen. Eventually you get down to the device that has the upset condition. A typical system like this has a couple of thousand screens defined. This is the visible part, the part of the automation system that the operator sees. And this is all background. I'm going to get to cybersecurity in a moment. The what a lot of people talk about is something called the Purdue model. Purdue model was designed by Purdue University 30-ish years ago as a way of talking about, giving names to pieces of lots of different industrial control systems. Industrial control systems are almost as old as computing. And anything that old, the terminology is arcane. And so they tried to rationalize the terminology by taking, computers in these control systems that had similar functions and similar characteristics and similar communications needs, and putting them into groups and calling them, level 0 is the physical process. In this example, the pipeline, the pumps, the valves. Level 1 are the computers that you can see on the bottom here. I don't know if you can see my mouse. They look a little strange, but these are special purpose computers whose job it is to monitor the physical process. They are electrically, physically wired into pressure sensors, flow sensors, temperature sensors, and of course the actuators for the valves and for the pumps and so on. So they call that, level 1. They called it the device layer, and there's many kinds of devices. You see some of the names there. Level 2 is the control layer. Sometimes it's called the distributed control system. Sometimes it's called the supervisory control and data acquisition system. This tends to be the system that has the HMI. Level 3 tend to be higher. So they gave this naming convention. And when cybersecurity became a thing post 9/11, the attack on the World Trade Center, when the world looked around and said, that was a failure of imagination. Where else have we failed? And came across cybersecurity for critical infrastructure. They said, that's a failure. And the whole initiative started in about 03, 02, 03, 04. They looked around and said, well, we've got to put firewalls in. We've got to segment these networks. It turned out that the Purdue model naming convention already had classified all of the similar devices that had similar communications needs, similar security requirements, and this became the natural segmentation model for industrial control systems, as well as the naming convention that had been used for decades. So, again, layers, and each of these you tend to see a many-to-one relationship. There's one internet, there's many businesses. There's one business network, there's many plants. A large power utility might have as many as 50 or 100 or sometimes 150 power plants. Each plant has many control systems. In a power plant, for example, a generating unit tends to have its own control system. If you have 5 generating units in the plant, you've got 5 control systems and 5 24/7 operator stations, one for each generating unit. Each generating unit has many PLCs and many devices, and each device has many controls. So it's many to one all the way down here. You get a lot of devices on the bottom. So that's background. We're talking as well about cybersecurity. The traditional cybersecurity presentation starts with threat. How much trouble are we in? The threat report, oh shoot, and there's a typo in there. That should be 2023-threat-report. We're still working on this year's. That's last year's threat report. I did a global replace for 23 and 24, sorry. We looked at, this is arguably the most conservative threat report on the planet. We looked at deliberate attacks, not errors and omissions, not equipment failures, not software bugs, deliberate attacks that caused physical consequences, most commonly a production outage, but there's been equipment damage. In theory, there could be loss of life. There hasn't been yet. Deliberate attacks, physical consequences in the industries we track, which is heavy industry, critical industrial infrastructure, and manufacturing, in the public record. No private disclosures. So I know this is an underestimate of what's happening because I've had incidents disclosed to me in private that I could not count here. Appendix B is half of the report. It's links to every incident we counted. For the whole decade, 2010 through 2019, the line was flat, bounced up and down between 0 and 5 incidents per year. Okay. Cybersecurity, cyber attacks on critical infrastructure were a theoretical problem. Governments were worried. Forward-looking industry was worried. The man on the street was going, why are we talking about this? Since the turn of the decade, though, we see an upward trend. In 2018, there was one attack with physical consequences. A semiconductor fab in Taiwan went down. In 19, there were 5. The headline was Norsk Hydro. In 2020, there were 18. Almost all of them ransomware. In 21, there was 23. Last year, in 22, there were 57. And, a sneak preview, we're looking at between 60 and 70 this year. So it's not a nice exponential curve. It smells exponential to me, but it's a noisy exponential. It might be something else. We don't know yet, but it's not theoretical anymore. We are seeing dozens of outages a year, and most of these attacks affect multiple sites. We're looking at over 200 sites affected in this year's statistics, and we're still crunching those numbers and madly writing this year's report. So the threat environment has changed. This is, if this exponential growth continues, we've got a crisis coming down the tracks at us. What do we do about that? Well, the first thing is to understand, again, the dimensions of the problem. You know, I've lost your name. Noelle, thank you. In her introduction said, there are differences between IT and OT systems. Some of them superficial, some of them fundamental. A lot of people talk about these differences. Patching is hard on OT systems. Antivirus is hard to deploy. If you run a full system scan and the HMI locks up, you have to shut down the physical process. You can't do that with antivirus. Even passwords are hard. If there's smoke coming into the control room and the operator has to remember a password to trigger the safety shutdown, I'm sorry, the operator's dead, because science has proven that we all become measurably stupider in an emergency. Our field of vision narrows, okay? Our cognitive facilities calcify. Some functions cannot be protected by passwords. These differences people have talked about since the beginning. Okay, in the beginning, 03, 04, when this initiative started, the engineering teams responsible for these physical infrastructures went to the experts. Who were the experts? There were only IT security experts. They went to the experts and said, how can we protect this infrastructure? And got an answer back that looked a lot like IT cybersecurity. Protect the information, protect the confidentiality, integrity, availability. In fact, you guys probably want to protect the availability of the information a little bit more. And they looked at these measures and said, this is hard. It's just a hard fit. And the answer they got was, yeah, it's a hard fit. Do it anyway. Try harder. This is all we've got. Today, in the last couple of years, people have started realizing, all of that, in a sense, is superficial. What drives the difference between IT and OT systems is consequence. What is the worst that can happen on most IT networks? There are always exceptions. That's broad strokes. What's the worst that can happen? Ransomware gets in there, steals our customers' information, leaks it out on the internet. Now we get class action lawsuits. We have to buy insurance for the victims of this personally identifiable information breach. And they encrypt all of our systems, and we have to bring in a guru and pay through the nose because these gurus we're bringing in on an emergency basis to clean this mess up. It takes days. It takes 2 weeks sometimes. What's the total cost? $15 million, $20 million. We can buy insurance for that. Okay, there are insurance companies will sell us insurance for that. What's the worst that can happen on an industrial network? Well, it depends on the network. A small shoe factory is different from high-speed rail switching. What's the worst that can happen on high-speed rail switching? Well, trains collide seconds after the compromise. Hundreds of people die. Mass casualty event. You cannot buy insurance for a mass casualty event. Most of the world's insurance companies won't sell it to you. They used to sell it to you 10 years ago. They don't anymore. And the trend is that nobody is going to sell you that kind of insurance. And even if you could buy the insurance, you get hundreds of people dead. Here's the difference between IT and OT. You cannot restore damaged equipment or the environment or human lives from backups. And so consequence drives all of these differences. Why is patching hard? It's because if you mess up the patch, you risk shutting down the physical process. Or in the worst case, you put safety at risk. You know, the first question engineering teams ask when they're told you have to patch your software, here's the patch, apply it. The first question they ask is, how many people will this kill? We don't know. How likely is it to kill anyone? We don't know. Until they have answers to those questions, they do not move a muscle. And when they get answers, the next question they ask is, how likely is this to trigger an unplanned shutdown? And, you know, modern software artifacts are complex. It's hard to answer those questions. Most engineers answer the questions with extensive, exhaustive testing, which is very expensive, takes a lot of time. The discipline is called engineering change control. We have to, you know, every change is a threat. Every change is a risk. We have to control the risk. We have to control the change. And so patching is hard because the consequence is unacceptable. And this is the difference. I use the word critical to describe a control system whose worst case consequence, if every computer in that system executes exactly the wrong instruction, tells the physical process to do exactly the wrong thing at exactly the wrong time, the worst case is unacceptable. It's human casualties. It's an environmental disaster. It's national security at risk. How could national security be at risk? Well, what's the definition? What's the legal definition of critical infrastructure? The word critical, the legal definition is critical to the nation. If we shut down the power grid, that is a threat to national security. That is unacceptable. And so, when we have unacceptable consequences, unacceptable threats to public safety is the obvious one. We have to do more. We can't just, uh, you know, protect the information. We have to protect the public. And so this is sort of a lot of new thinking that is crystallized around an initiative called Cyber Informed Engineering. This is funded by the Department of Energy. It is being executed by the PhDs at Idaho National Labs, and it positions OT security as a coin with two sides. One side of the coin is cybersecurity. Teach engineering teams about cyber threats and about cybersecurity tools and techniques. The other side of the coin is engineering. We're talking about threats to safety. If, everyone listening here, imagine that every one of us is a technician in an old school coal-fired power plant. How does a coal-fired power plant work? Well, you've got 5 massive generating units. Each one, you've got coal that's crushed into powder. The powder is blown into a furnace. It ignites instantly. A second later, it's consumed, converted into heat and carbon dioxide, which we want to get rid of, and water vapor. Heats a massive boiler, 5 stories tall. The steam in the boiler drives a steam turbine, turns the turbine turns the generator, produces the power. Every one of us is the technician responsible for these 5 boilers. We calibrate the instrumentation. There's countless measurement points all over the boilers. We replace the measurement instruments when they fail. We have the gamma ray testers to test in situ for corrosion and the strength of the boilers without shutting anything down. We work all day within the worst case blast radius of one of these boilers. If one of these boilers blows up, we're dead, and so is everybody else nearby. How would each of us like to be protected from a cyber attack that overheats the boiler? Well, would you prefer a mechanical valve where the steam, pushes against a steel plate? If the steam pressure becomes too great, it forces the plate against a spring, the steam escapes and there's no explosion. Or would we prefer a longer password on the computer controlling the furnace? Most of us would prefer the mechanical valve, thank you. It's not hackable. It has no CPU. It behaves deterministically. When I asked this question of experts, they say, Andrew, you're being deceitful here. You're asking the wrong question. The question is not, do I want the mechanical valve or the password? It's my life on the line. I want the mechanical valve. I want three of these things because they're mechanical. They can rust, they can wear out, they can fail. I want three of these things and the longer password on the computer and a boatload of cybersecurity beside it. And that's cyber-informed engineering. It's not that you're choosing one side of the coin or the other. You need the whole coin. We need cybersecurity and engineering both. But here's the thing. Where is the overpressure relief valve? Where is the centrifugal overspeed governor? Where are these electromechanical devices in ISO 27001? Not there. No mention of them. In the NIST cybersecurity framework, no mention of them. In the industrial 62443 standard, where are they? They're not there. These are cybersecurity standards, not engineering standards. What we're talking about is safety engineering and protection engineering and automation engineering. These disciplines have powerful tools for managing physical risk. The risk of an earthquake crimping the output valve on the boiler, letting no steam escape anymore, and the boiler overpressurizing. This is the kind of threat that these devices were designed to address. But increasingly, they can be used. There are scattered pockets of engineers who are using these mitigations for cyber threats as well as physical threats. And cyber-informed engineering is saying this belongs as one coin. We need these engineering tools that only exist in the OT space. They have no analog in the IT space. We need these engineering tools to be used universally and systematically wherever they apply to protect public safety, to protect national security. And this is, what I wrote about in my most recent book. I've, coined the phrase engineering grade. What is engineering grade? Give me a moment. Let me do a time check and see how much trouble I'm in. Oh, okay. Well, I'm in trouble. So, let me just say engineering grade is deterministic, is these are devices whose failure modes can be modeled mathematically. Um, I have to give you the example. Imagine a bridge. Most of us have heard about the Tacoma Narrows disaster, one of the world's first large suspension bridges. 1940, bridge tore itself to pieces because a stiff breeze came up and the engineers of the day had not figured out harmonic frequencies. The bridge started oscillating more and more, building up with a harmonic frequency until it tore itself apart. Imagine that today's engineers have figured out how to build bridges, I don't know, carbon fiber or something, at 1/3 of the cost. Suspension bridges at 1/3 the cost of everybody else's suspension bridges. The problem is the design is riddled with um, harmonic frequencies. And so the engineers of the day have deployed active vibration dampers. The bridge feels rock solid because every small vibration is being actively dampened out by computer-controlled dampers, multiply redundant, triply redundant power supplies. AI is controlling the whole thing. How happy would you be driving across that bridge if you knew that the design engineer hoped that if a cyber attack targeted the AI, we could detect the attack before it crippled the dampers? How happy would you be driving across that bridge knowing that the design engineer hoped that if we detected the attack, we could scramble the incident response team in time to prevent the compromise of the AI? Hope is not what we expect of the engineering profession. We expect a bridge to carry a specified load in a specified operating environment for a specified number of decades with a large margin for error. That's what we expect. And this is cyber-informed engineering. It's starting to take these engineering principles, not for small shoe factories. When public safety is at risk, apply these principles systematically to the design of cybersecurity and protections, other protections for industrial control systems. Something that's a little bit new. A lot of the pieces of this puzzle are old. cyber-informed engineering has invented comparatively little that's new. What they've done is rearrange the puzzle pieces so that there's no space between them anymore. I've related, this stuff to owners and operators of critical infrastructure, and they looked at it and said, that makes so much sense. They said, why is this new? Why have we not been looking at the problem this way for the last 20 years? But it is new. It's a new way of looking at the old stuff. Something new is a term. I mean, the one thing I do invent is terminology. If I hear different teams calling the same thing or converging on the same idea from different directions with different terminology, I'll make up a term. I've made up the term criticality boundaries. I've made up the term network engineering. In my definition, network engineering is the discipline of managing criticality boundaries. These are connections between networks at dramatically different kinds of consequence, dramatically different, critical networks with unacceptable consequences versus business networks with acceptable consequences. When you connect those networks, you have to do things differently. There's a whole chapter on what are the techniques available to make those joins. A concrete example is the EPRI Internet of Things methodology. EPRI is the Electric Power Research Institute. Again, a bunch of PhDs. They do research for the electric sector. They were tasked back in, I think, 2017 or so to answer the question, we want to use the Industrial Internet of Things to monitor our turbines so the vendors can predict when they're going to fail and optimize, give us efficiencies in terms of maintenance of these very large, very expensive devices. We're talking $300-400 million per turbine. And they came back, and we cannot accept threats to the operation of these critical infrastructures. And they said, they went away, they looked at it, they came back and they said, here's what you do. Get your measurement devices, the vibration sensors, the heat anomaly sensors, whatever. Do an engineering study. Prove to yourself that these devices are physically monitor only. They're not physically able to control anything. Convince yourself of this. Deploy them on your turbines. Do not connect them to your control network. Connect them to a DMZ on the IT network, out to the internet, out to the cloud. A lot of these devices, you can put SIM cards in. Put SIM cards in and connect them straight out to the internet, because the consequence of compromising these devices should be a business consequence. We maintain the equipment suboptimally. It costs us an extra $300,000 a year in maintenance. That's a business consequence. We can buy insurance for that. Do not connect these things to your control network. Because if you do, and the attackers get into the cloud system, they can pivot through the cloud system into these devices and pivot through these devices to target the rest of your control system and cause unacceptable consequences. So I thought, brilliant. This is brilliant. The thing is, if you have to connect them to your control network, because that's all you have, well, now you've got a problem. And this is where Waterfall comes in. This is the one slide, plugging Waterfall. We produce a technology that fits in the middle of this network engineering space. It's a technology that is becoming more and more widely recognized at criticality boundaries. You don't use it inside the control system. You don't use it in the enterprise. It's used at criticality boundaries, which is why I care about network engineering so much. Really quickly, it's called a unidirectional gateway. You can Google it if you want. It's a combination of hardware and software. NIST defines this class of technology as hardware that is physically able to send information in only one direction. Think a fiber optic transmitter on one side, a laser on the other, and that fiber between them. You can send from one to the other. It's not physically possible to send anything back. This is engineering grade unidirectionality. There is no laser in the receiving circuit board. It's not a transceiver. It's a receiver. And there is no receiver in the sending circuit board. So one way out, and the software makes copies of stuff. So if you have, a database, let's say a historian database or even an Oracle database in the industrial network that is gathering all of the data that we want to share with the business for efficiencies, the software in the gateway logs into the database, gathers the last second of data, everything that's changed in the last second, pushes it out through the weird one-way hardware, and populates an identical database on the outside network. The business systems that need access to it can grab that data from the Oracle system on the enterprise network. All of the data that's allowed to be shared with the business is out there already. I have 5 more minutes. Let's hit this one real quick. What is risk? Risk is abstract. Risk is boring. Nobody wants to know about risk. Risk is consequence times likelihood. Really, that works for, low, call it, low consequence, high frequency threats. How often on a large, let's say 100,000 employees, how often does someone download a bit of ransomware and encrypt part of the network? Well, it happens probably a dozen times a year. Okay, so we're not talking consequence times likely. What's the consequence? It costs $150,000 to clean this mess up every time. Risk is $150,000 times the frequency with which these low impact events happen. How many times has the entire North American grid been knocked out by a cyber attack? Never happened. So what's the likelihood? Well, nothing is ever perfectly secure. Security is a spectrum. The likelihood is very low, but any kind of number we put there is made up. And here's the thing, business decision makers who are sitting on the budgets for cybersecurity programs, they don't like making funding decisions based on made up numbers. So how can we spring the funding loose? How can we justify what we're doing? To me, the gurus that I talk to say, Andrew, you should be modeling cyber risk as the same way that you model physical threats like terrorist attacks. It's a function, okay? It's not times. It's a function of consequence, intent, opportunity, and capability. And the way it works is if there's intent and the bad guys' capabilities, attack capabilities, are greater than the capabilities needed to exploit residual opportunities, because there's always attack opportunities in our infrastructure, then you will suffer the consequence. If there's intent and the capability is greater than the capability needed, we're going to go down. It's deterministic. And why is this useful? It's because with this model, the question becomes, how capable are each of our enemies? And what kind of security system, what kind of residual risk can we tolerate? And we express that in terms of the simplest attack that causes unacceptable consequences. So I'm freaking out because of the time and I'm not making sense. Let me give you a concrete example. Design basis threat for an embassy in a hostile region is going to say something like, now these things are classified. I've never seen one of these, so I'm completely making it up. I'm guessing it'll say something like, the embassy's security program will reliably defeat an attack by up to 6 terrorists armed with submachine guns and hand grenades, trained for 3 months at this camp in Iran. Reliably, you will defeat that attack reliably. You're not required to defeat a squadron of tanks driving down the street, blowing holes in buildings. You describe the most capable attack that you're required to defeat reliably. And everything else, well, you do what you can, but you're not required to defeat that. Design basis threat makes sense in the cyber world. And, something I did not say on the threat side, a lot of the ransomware coming after us nowadays is nation state grade. We have nation state grade adversaries coming across the internet, coming after our money. Some of the ransomware is backed by nation states. North Korea is accused of backing their ransomware groups to make money for the sanctioned regime. And some ransomware groups are just so wealthy they can afford nation state grade attack techniques. So we need to protect operations from nation state grade adversaries across the internet. But if I'm running a small water system in the town of Brooks, where I was raised, 15,000 people, 10,000 subscribers, How much does the average subscriber pay in a year? $1,000 for water and wastewater. We're talking a $10 million a year budget, almost all of which goes to paying people with trucks and backhoes digging holes in the ground. Do they have an IT person? Maybe. Do they have an IT security person? No. Do they have, you know, this is a problem. Cybersecurity is a problem. But on the other hand, is it credible that the Russians are going to plant 3 people in the town of Brooks water system as a sleeper cell and activate them in 5 years' time to cripple the water system for the? That's not a credible threat. Okay, we need a nation state grade design basis threat for network based attacks. We don't need that for insider attacks. So this is a tool that we can use, and I talk about in chapter 7 and chapter 8, that we can use to figure out, the city of Chicago might be a credible target for a sleeper cell. The town of Brooks is not. So um, I'm up against the time. I had a slide on insurance, but basically insurance is changing. I've said some of that already. About waterfall, we invented unidirectional gateways. We're deployed throughout most of the developed world. We're trusted by critical infrastructures all over the world. This is why I care so much about network engineering. And this is the bottom line. I am shipping some books, physical books, to you folks. They haven't arrived yet. You're welcome to, free copies of my latest book, Engineering Grade OT Security. It talks about public safety. It talks about the spectrum of what we have to do on the low end versus what we have to do on the high end. I haven't said much about the low end. What do you have to do for a small shoe factory? What's reasonable? Um, buy insurance. Do whatever the insurance company tells you. Make sure that if you submit a claim, you can pay it out. You get there, they're going to pay it out. That's a reasonable thing to do if you've taken worker safety threats off the table with engineering grade electromechanical mitigations, and you can do that. The threat load is going up. We have a problem. And the pervasive threat across the internet is nation state grade. We have to raise the design basis threat to that level at most of our industrial sites, large and small. Criticality boundaries demand network engineering, demand engineering grade prevention of attacks propagating into networks with unacceptable physical consequences. And design basis threat is a useful tool for modeling threat rather than the murky likelihood and consequence. Consequence you can quantify. Likelihood, it's a poor model. It confuses decision making, and I argue that design basis threat is a better one. That's what I had for you, a lightning tour of the OT space and the cybersecurity space. I'm grateful that you can't send tomatoes through the teams. I'm open at this point to criticism and questions.
Great. Thank you so much, Andrew. That was, you have a lot of information in there. And I think an alternative to Asifa for a question, I think what's great is the, not the technical details of coding, but understanding the social engineering, the public safety, some of the goals around the OT groups that are different, like you said, in the IT groups. So Asafa, would you like to ask a question?
Oh, yes, I do. Thank you very much, Andrew. That was fascinating. I had noted down a few things in my head, but I don't have time. So I'll ask maybe the one that I thought would be something I can comment on. The technology that you said, unidirectional, very, convincing in the sense that you are securing by making sure that there isn't anything coming the other way. And so that way you have safeguarded. It just intrigued me whether there is something like a similar idea that is used somewhere else, that you could say it's not just about now physically protecting something that you have designed, but it is also in a systemic way to think about it, has got bigger consequences than the actual device that you have created. Can you comment on that one?
Absolutely. So let me do two things. I'm going to talk about cross-domain, and I'm going to talk about the title of the piece here. I never actually circled back to ask different questions. To your question, the unidirectional. Our customers do not ask the question, how do I protect the information? If you ask that question, the knee-jerk reaction is quick encrypt everything. The problem is I can pull an attack inside an encrypted connection. Encrypting the attack doesn't help you. The goal is not protecting the information. The question that I observe our customers asking is, how can I protect physical operations from information? More specifically, from cyber attacks that may be embedded in information. Not how do I protect the information, but how do I get protection of physical operations from information? That's one of the key questions they ask differently. But to your question, yes, the concept of unidirectionality is actually much older than the industrial application. The industrial application emerged in sort of the early noughts. The concept of unidirectional communications has been used back as early as, I think, the 1980s. What's the criticality boundary there? It's between public networks and classified networks. If you leak the names of your spies out of your classified network into the internet, they all wind up dead or in jail the next day. Okay, this is completely unacceptable. So yes, there are consequence boundaries in networks where you're protecting the information. Don't get me wrong. You need to protect the names of your spies. Okay, you need to protect the designs for nuclear weapons. Okay, in some networks, information is the asset. In other networks, physical operations is the asset, and confusing that messes things up. And what I'm trying to do is make that clearer. But I hope that answered the question.
Yeah, it does. Very quickly, and you can answer this one very, very, very quickly. The math part intrigued me, where you said model, the consequence, and there were 3 or 4 other things. What does that function look like? So is it just a simple thing you add, some of them are squared and so on, or is there deeper mathematical?
There's deeper. It's a sum. I don't put all of the symbols there because it scares people, and people are scared of risk to begin with. So it is the sum across all consequences, and all threats and all opportunities of bang bang bang.
Okay, thanks.
So it's 3 nested sums is my read on it. I haven't done a lot of analytical work on that. I do have a math background, but it's a long time ago.
All right.
I try to work in the concepts.
Thank you very much, Andrew.
Great. Ben, you had a hand up?
Yeah, I did. I'm realizing that my question might be a little bit out of your realm of industrial controls. I was considering utility in my mind as like industrial, but I'm thinking that it's not quite under that. But I'm looking into this curious problem where we're having more and more renewables being injected into our grid, and that's moving the ownership of our power source from either utilities or utility partners, which would be industrial generation sites. It's moving the ownership into a distributed form of these renewable energy output, like wind farms, just the PVs that you would put on top of houses. I was wondering if you guys have done any thought or work on finding standards on how to protect against those kind of attacks, because those so for instance, I went and I found a website that tells you all the exposed ports on the internet when you type in a search thing. And so I searched for the first inverter I could think of, and there's hundreds across the US of this inverter exposed. And so more and more as these get installed, it's going to be a critical infrastructure problem. And it's hard to define where the responsibility lands because it's kind of a utility industrial problem. It's kind of a individual consumer problem. So I'm not sure what that looks like, but it's just as dangerous, I think, and worthy of thought.
It's a problem, and part of why I'm interested in presenting this in this forum is because you folks are tasked with inventing solutions to hard problems. So let me phrase the problem a little bit more. We do deploy unidirectional gateways. Our gateways are sort of rack mount devices. We do deploy them on wind farms, sort of a device that connects the wind farm to, less consequential networks. We generally don't deploy a rack mount device in consumers' homes for their rooftop solar. There are vendors out there with devices as big as my fist that do unidirectional protection for rooftop solar. So the idea is something that is being applied, in surprising ways in surprising number of places. We're starting to see automobiles with devices that are this big, unidirectional between the safety critical networks and the entertainment network, for example. So yeah, the technology has widespread applicability, but there are entirely new problems, and there's a working group out of Idaho National Labs that I've signed up for and missed the inaugural meeting, but they're looking at cloud systems, because cloud systems are increasingly involved in managing charging stations, in managing solar. If it's all about efficiency. It's all about return on investment. Increasingly, homeowners can connect their solar into an aggregator. Someone like, I think it's Google, but I'm not sure. Someone like that is signing agreements with lots of homeowners, aggregating that solar power in a geography into, in a sense, a single logical, a virtual asset in the cloud, and interacting with the power grid as if it were a single large generating asset. And bluntly, you make more money that way. Here's the problem, though. This is a cloud system. If you break into the cloud, and it's possible, now what happens? Well, I haven't even figured out what are the possible consequences. Much less how would you defend against those consequences? Are those consequences acceptable? Again, this initiative at Idaho National Labs is basically got a nebulous mandate saying, look at cloud systems, look at the power grid, figure out how much trouble we're in, and try and make some recommendations. To me, the good news, one of the things I try to do with the book here is raise awareness of the need, raise awareness of alternatives, and create demand for engineering grade solutions. Because if the demand is there, people like you will be tasked with, well, the industry is demanding X and it doesn't exist. Let's build X. Let's try out 17 different ways, pick the most effective. You get innovation. This is a driver for innovation, but the demand has to be there first. And if you don't understand the problem, if you can't see the train coming down the tracks at us, the analogy I use is, this exponential growth in outages is a train coming down the tracks at us. I don't believe that we can build a cybersecurity wall big enough or strong enough or fast enough on that train to stop that train. I think we have to get off the tracks. And here are some ideas for how to get off the tracks. And if we can create demand for this, there's opportunity for innovators like yourselves to meet that demand and make us all safer.
I see. Yeah, thank you.
There was another hand up, but I don't know if the person had to leave. We do have one question in the chat. Maybe we could take, and then, and I will remind everybody that for Cyber students, the survey is in the chat. So please take the survey for us. You mentioned that you make a one-way router of sorts to shield industrial IoT devices, but what about when the data goes beyond the boundary of that device?
My guess as to the meaning of that is the data has value. I've talked about the engineering priority being protect public safety, yes, but if we're building aircraft parts, okay, the robotics programs that craft those parts out of raw metal are very valuable. If we're producing pharmaceuticals, the recipes for those pharmaceuticals are very valuable. And some of that very valuable information, there's a risk of it showing up in the business systems and being exposed. Within the boundary of the plant, we tend to be focused on safety and reliability. Within the boundary of the IT network, it's their job to protect intellectual property assets. And so when the information leaves the device into the IT network, then what? And we get this question. It's a good question. I'm sitting at a boardroom table, making the pitch, and I get the question, and I look around the table and I say, well, we are experts in the boundary with the unacceptable, the critical network. You sitting there are in the enterprise security team. You're the experts on protecting information, not us. How would you like to protect that information? Well, they say, we would like these replica servers, the Oracle server I talked about, or OPC or Pi Historian, whatever it is. We want those replica servers to sit in a DMZ. We want a firewall on the outside. We want two-factor authentication. We want encryption. They apply cybersecurity techniques that are used routinely to protect information, to protect that information at the boundary where it comes across the criticality boundary into the enterprise network. And we say, you go for it. Whatever you need, we support. Our software is on that side of the device is designed to meet the demands of the IT teams that are consuming the information in their business automation.
Well, great. I think that's all the time and all the questions that we have. Thank you, Andrew, so much for a great talk on a lot of important topics as we think about cybersecurity and the future. So we really appreciate your time and effort and look forward to having your books and being able to learn from those. So thank you, everybody, for joining us today. Again, for the students, please make sure and go in the chat and find your and find the survey and do that before you head away. Thanks, everybody. Have a great week.
Thank you so much.
Andrew. Thank you, Andrew.
Thank you.
Bye-bye.